Welcome, everyone, to today's JMP Academic webinar, Teaching Categorical Data Analysis with JMP. I'm Ross Matusalem, a JMP Academic Ambassador, and I'm just here to host today, field some questions in the Q&A. Our presenter today is my colleague, fellow Academic Ambassador, Kevin Pochner, and Kevin is going to be showing us some tools and techniques for using JMP to teach categorical data analysis in the classroom. So whether you're teaching a course entirely focused on categorical data analysis, maybe in a statistics department, or maybe you're teaching a more general or discipline-specific course that incorporates categorical data analysis in some way. Today's webinar should show you all the things you need to know to be able to use JMP effectively in your course and with your students. Before we get started, I invite you to ask questions throughout the webinar today. When you do, please type them into the Q&A panel in JMP. You'll find it in your Zoom interface under the speech bubble icon that I have displayed on the screen there. Using the Q&A just helps us keep track of the questions and which ones have already been answered a little more easily than the chat. So please do feel free to use the chat to make general comments or to chat with each other during the webinar. But for questions that you would like myself or Kevin to answer, please use that Q&A. And so with that, let's get started. Kevin, are you there?
I am.
All right, take it away whenever you're ready.
Okay, just can you confirm you can see my screen?
It's looking good.
Okay, perfect. All right, well, welcome everybody. Let me just show you the agenda on what we're going to cover today. Obviously, when we talk about categorical data analysis, we're talking about the outcome variables categorical, as I'm sure you know, and we often talk about different types of categorical data. And so the classic one that's used a lot is binary data, right? So that's typically in this sort of yes, no, or pass, fail, or some characteristic exists or it doesn't exist. And there's techniques that are designed specifically for binary data. There's also nominal data where we'll have categories and there could be more than two categories. So examples there are like maybe the products a customer purchases or the department some employee is in. These are categories, but there's no order to them, right? So in those examples there, you can see it's not as if one is better or worse than any of the others. We do have that kind of data too, as many of you probably experience, and we call that ordinal data. And so something like, oh, maybe the level of damage to a product or something in a test might be mild, medium, or severe, or we have an opinion in polls, and that you probably have done these before, where you've got strongly disagree to strongly agree, or maybe income, and we put it into categories like that. Now that last one is good to point out because it's common that you might have data that's originally numeric continuous, like income truly is, but for the purpose of a specific analysis, it makes more sense to put it into groups. So age is another one. And so that's common because it just might simplify something you're doing is to put it into categories. So I'm going to talk about one sample and two sample inference for proportions. That's something that's covered in almost all introductory statistics courses, whether it's for stat majors or social science majors or engineering majors. This is pretty common. So I'm going to show tools in JMP to do that. Then I'm going to show an example where we're going to test for independence of a categorical variable across some factors. So that's basically contingency table analysis, or sometimes it's just called chi-square analysis because that's one of the tests that are common to do. It's not the only test that's done, but it's a common one. So sometimes people will just call this chi-square analysis. I'm going to talk about logistic regression. And that's where we have a categorical outcome. It could be binary, it could be nominal, could also be ordinal, but just treating it as categories. And the factors, sort of the explanatory variables, are continuous numeric. So the chi-square one, the contingency table, that's where the outcome and the factors are categorical. I'm not going to have time to show other modeling techniques that JMP has to analyze categorical outcome data. I'm going to focus on logistic regression, but I'm at least going to mention it. And these techniques have become popular in the past couple of decades, where for many, many decades, everything was logistic regression. And now there are other techniques. So I want to make sure you are aware that JMP has those. And I'm going to end with an example. We have an actual platform called Categorical that's inside of our consumer research, because this is often done in those kinds of applications. This is basically like cross tabulation, right? Where you're gonna build tables that have many factors, and you're gonna look to see if there's differences across the various categories. Now, the data I'm going to use for all of this, except the last one, the survey one, is one of our case studies. Actually, it's a set of case studies. If you are not familiar with our case studies, I strongly encourage you to go there. You will find these very useful to use in a course. We've got 60 different case studies that cover a wide range of applications. They have a range of difficulty from basic to pretty advanced. And you can see on the right, it tells you the statistical tools you're going to use, and also the applications there in the middle. I'm going to be using, I just passed it. I'm going to be using these right here. And this is where the example is about an engineering team testing the durability of mobile phone screens, right? You'll see when I open it up, they're going to do a drop test. So inside of the journal file that you'll get later, if you go to download the recording, you'll also be able to download this journal. And from here, I've got a couple links that I just want to point out to you. There's a help documentation for these various techniques. So if you click on that, I'm not going to do that, but if you clicked on that, it's going to launch our help menu to that particular platform. And so that's where you can read and learn more about it. And then this link here, this case study, will send you to that specific case study where you can download that along with the data. But I'm just going to open them up here. I already downloaded them. Okay, so this example is about a company that manufactures mobile phone screens, and they want to test the durability of them. This actually comes from an example I did out in industry, I think maybe almost 2 decades ago. It was for the actual case of the phone, but it's the same idea. So basically what's going to happen is there's 2 screen types, A and B, and they're going to do an experiment where they drop 10 of them of each type, and they're going to do that from a 1 meter height. And then they're going to record a binary variable if there was a success or a failure. In other words, the screen was not damaged versus the screen was damaged. Now, if this was, if you're really working on this problem, what would be better than a binary outcome would probably actually be, well, either nominal or maybe even ordinal, right? Where you can say the damage is mild, medium, or severe, or maybe just different types of damage, like a crack, a fracture, shatter, So we're treating this as binary, but it might be better if this was done in practice to do something with a little bit more detail. Now, there are 2 sort of questions that this team has that they want to analyze this data for. One is they're hoping to demonstrate that these screens have a 97% reliability. In other words, that if you did drop like many, many screens, a whole population of screens that they manufacture, that 97% or more would not be damaged. So that's a success rate. This is very common in companies that manufacture things. They want to demonstrate that they have a certain level of reliability, and that they have to test some screens to do that. So we're going to look at that. And then since we have 2 types of screens, A and B, we're going to do a comparative analysis to see if there is a difference in their performance. Okay, so let me go ahead and open up the data set. All right. So you'll notice that this data is in a table format. So instead of having 1 row for each screen that you test, you'll see that it's sort of paired off. So for screen A, we've got 2 rows. We've got the 2 outcomes, fail and success. And then over on the right, the frequency variable, that's telling us the count for each of those. And then, so you can see 10 screens were tested. None of the screens have failed for type A. And then if we look at B, you'll see that, yes, we also tested 10 screens and one of them failed. Okay. Now, this is you'll see that this way of organizing your data can be very useful, especially in this categorical approach. Now, I'm just going to open up another data set, or sorry, it's the same data, but just another JMP file. So this is the other way you can have the data saved, where each row is one of the particular screens that were dropped. And if you look at this, you can see, this is in a random order because the test was done randomly, but you can see there's only the one failure right here for screen B. Now, with such a small data set, it's not a big deal to have it in either way, but you'll see when we move on in the examples and this case study tests more and more screens, you'll see that this frequency table approach is actually a handy way to use, do base the analysis on. Okay, so we're going to start off with one sample inference. And what I want to do based upon this sample of test is estimate what the population proportion is going to be. And so if you're not familiar with using JMP, when you want to do a univariate analysis, and it doesn't matter if it's numeric continuous data or categorical data, you launch this platform called distribution. And what I'm going to do is, now this, if you haven't seen and worked with data in this table format, it is a little different how you fill it out. So the outcome variable, that's your Y, right? That's where it's saying success, fail, success, fail. Again, there could be more than 2 categories, but we only have 2 here. And you put the frequency here. And since I have 2 screens, A and B, I'm going to use that as the by variable. And so what I'm going to get is a univariate analysis for the results from screen A and a univariate analysis for the results from screen B. So I'm going to click OK. And what JMP does in every analysis is it starts off with some initial output. And so here we're just getting a summary of screen A and B and seeing a little bar chart as well as some counts and proportions over on the right. Now, what is common that I've seen out in industry is someone might look at this and they'll say, oh, we demonstrated 97% reliability for screen A because notice we have 100% success. And that's naive because remember, we're only testing a sample here. We're doing inference to a population. And this particular problem that I had worked on many years ago, they were doing this. They would only test a small sample and then believe they reached some reliability just because the sample did. Well, if you want to make inference to a population proportion, we can add a confidence interval to this. And so when you drop down the menu in the red triangle, you can pick some confidence levels that are already defined there, or you can click other and pick a different one. But since 90, 95, and 99 are so common, we've got them listed there. So, oh, I should point this out. I don't know if any of you know this, but if you're going to do the same, you're going to choose the same option for a bunch of different variables like I'm going to do here. If you hold, oh, this is, I don't know what it is in Windows, but in Mac, it's the command key. If you know what it is, Ross, maybe you could type that in. If you hold the command key when you come down here and select an option, what it's going to do is it's going to do that analysis for every, in this case, every variable that's in that report. So you see how it produced the confidence interval for both. Otherwise, I would have to go here, do it, and then go down here and do it. But this allows me to get them all. Now, if we were to look at the confidence interval, so we'll look at the one for A first. If we incorporate sort of the uncertainty, because this is just a sample, really all that we can say is that we believe the success rate for a population of screens that would be dropped from 1 meter is, it could be as low as 72%. So we haven't demonstrated that 97% reliability. We would need that lower bound to be greater than 97. Now, if I go down to B, remember B had 1 failure, we can see that a 95% confidence interval is showing us that the success rate could be as low as 60%, and it could also be as high as 98%. So it is possible the reliability is achieved, but certainly we cannot reach the conclusion in these data. Now, I don't need to do the hypothesis test because this confidence interval gave me that answer. But just to demonstrate, I'm going to go down here and I'm going to show you how I'm going to do this. So I guess I did that kind of quickly. But if you if you click the red triangle, you'll see test probabilities. And when you do this over here on the right, then this little appears for you to type in this case, I'm going to type in the this case, the success rate, right? This is what I'm testing in my hypothesis. And my alternative is that it's greater than. So what I'm going to do is going to put 9.97 greater than, and then I'm going to go done and done. And then what you're going to get is the results of a hypothesis test. And as expected, we don't have the evidence to believe the alternative hypothesis that the proportion is greater than 97%. We don't. Now we knew that already from the confidence interval, but I just wanted to show you that that's where you run that analysis. Okay, now in our case studies, again, if you haven't seen these yet, I really encourage you to take a look at them. So what will happen is we'll demonstrate some analyses, and basically this one is doing the analyses I've just shown, as well as some others. And so you either demonstrating in class or the students kind of doing on their own, they can walk through this, it interprets the results, it shows the jump steps and everything. And then when you get to the end, there's a set of exercises that you can hand out for, maybe a team project assignment. If you want the solutions, when you go to the case study page, you'll see there's a little link to say request solutions. You click on that, and we just need to verify that you're faculty and you're not a student asking us for the answers. And then we can send you the exercise solutions for any of our case studies. So what happens in this particular case study, and I'm going to move along, but before I do, Ross, I just want to check, is there anything that came up that I need to address?
Thanks, Kevin. I think we're in good shape now, so feel free to continue.
Perfect, thanks. Okay, so part 2 of this case study is based upon the results. Oh my God, I forgot to do the 2 sample one. Please let me go back to that. Apologize. 2 sample inference. Sorry. So here I want to compare if I think there's a difference between the success rate for A and B. I understand there's 90% and 100% in the sample, but I want to generalize to the population. So when you're doing a bivariate analysis in JMP, whatever that bivariate analysis is, you're launching our Y by X platform. And remember, we have the data in this frequency table format. So the Y response is the outcome. You're putting the frequency there, and then screen is the X factor. Now, remember, there's 4 sort of scenarios you can have here. You can have a categorical outcome and a categorical X like we do here. And in that case, that's a contingency table analysis. If you have a categorical Y and a continuous X, then that's logistic regression. If you have a continuous Y and a continuous X, that's linear regression, and a continuous Y categorical X, that's ANOVA. So you don't have to pick that. You just open up this bivariate analysis platform, and you will JMP will know to run the right analysis. So you click OK, and JMP's going to start off with a mosaic plot that's showing the proportion of success and failures in the sample. We can see that here. We also have a contingency table shown here, and you can choose what information is this in this contingency table. So maybe if you're teaching in this in class and you're trying to get students to understand what is a chi-square analysis, you might add some more things here, like, oh, I'm going to add the expected. I'm going to add the deviation from the observed to the expected, and maybe the chi-square value for each of those cells that produces the test statistic. You might add that, and so you can turn these on and off. Oh, I should show this. And again, I don't know what it is in Windows because I have a Mac, but if you hit the Option key when you click a red triangle, any red triangle, it actually pulls up a window that has all the items in that menu. And so this allows you to select the things you want all at once instead of what I was doing, which clicking, then red triangle again, clicking. So wanted to point that out. Okay, so down at the bottom, we're going to have some results of this comparison between A and B. And there's a couple different tests there that are common when you're doing the contingency table analysis. Now, since I only have two categories here, if I drop down the red triangle, I can do a two sample test for proportions. And so I'm just going to add that result here. And when I do that, I am going to get the results of via a confidence interval. And as most of you are going to know, if you look at the confidence interval, in this case, it doesn't contain, or it contains 0. So it looks like, oh, maybe A is better than B, or maybe B is better than A. I don't have something conclusive to believe one is better than the other. So you can either look at the confidence interval, or JMP also does test, and it's doing every possible alternative, one-sided or two-sided. So it's showing them all there. You can also click on the, if you want to phrase this in terms of success, you can do that, or failure, you kind of have that option there. Now, something I always kind of had an issue with comparing proportions and doing it as a difference, because when you're interpreting it, someone might say, oh, this is 34% either smaller or 18% bigger, but that's not actually true. It's not a percent. You're actually looking at the delta between 2%. So it's on a scale that's not really a ratio to create a proportion. So I'm a fan of actually doing relative risk. So what that basically does, it's the ratio of the two proportions. So I'm going to click on that. Again, I can pick, do I want to phrase this as failure or success? And what do I want to put in the numerator, A and B? I can also pick all combinations. I will do that just so you can see all the results we get. Now, down the bottom, we're going to get those looking at the ratios. Now, some of them you can see don't produce the answer, and that's because 0 ends up being in the denominator for some of these, right? Because we only have we have 0 successes for 0 failures for screen A, but I'll look at the ones where 0 isn't in the denominator. And so if you're looking at a confidence interval for proportion, a ratio of proportions, if that ratio is 1, or you believe that ratio is 1, then that's saying that A and B, the proportions of A and B are the same. And then if you don't believe it's 1, then that's concluding something is either bigger or smaller. I like this better because when you go and look at, for example, that number, you're actually saying that it's 90% smaller than, and this is 37% bigger than. They're actually percentages versus the two proportions where these aren't actually the percentages. I understand they're percentages, but they're not the percentages of one versus the other. This one is not done as much in introductory statistics classes, but I wish it was, because I think that's a better way to approach proportion problems. Okay, sorry, I skipped that. So let me get back to the second case study here. So what's done now is, well, they want to do more tests. And so what is done in this case study is they actually go and test 40 more of screen A and B at that 1 meter drop height. But they also have a third screen that they want to include in this study, and that is screen C. So they test 50 at the 1 meter drop height. And then what they also do is they say, hey, let's go and test these at the 0.5 meter drop height and at the 1.5 meter drop height. So they're really expanding this. And that was kind of from the result of case study 1, where it's like, okay, we didn't really have enough data to, see any kind of difference or conclude that we reached a reliability. So that's why this one expands to conclude that we should do more testing. Okay, so let me open up that data set. And so again, this is in that frequency table format. So you'll see we've got screen A at 0.5, screen B at 0.5 meter, screen C at 0.5 meter, then all at 1 meter, all at 1.5 meter. Now, you might also notice I actually added this column where I'm showing how many were tested, and then I'm showing the rate. for the failure and success. You don't actually need to do that. You don't need those two columns, but I just did that because sometimes for certain graphs, I might want to actually use this rate. This is very easy to calculate. You just need to create a formula. So if you double click on a new column and drop down column properties formula, edit formula, then I'm going to go in here and grab my columns here. Then I'm going to say, well, it's the count divided by tested, and I click OK, and then I'm going to get those rates in a new column. I sometimes like to do it because when you look, it's easier to see. You don't have to actually look at the calculation. You can quickly see that proportion. Again, JMP doesn't need you to do that, but I find that handy when looking at the data and also creating some graphs. So let me go and I'm going to do now I could go and, well, maybe let me start off with that. I'm going to do the one variable at a time, a univariate analysis first. I got 3 screens. And so if I did this, I'm going to get something similar to what I did when I only had 2 screens. And again, I can go in there. And if I want to produce confidence intervals, I can do that. Now, if you look, actually, you'll see the lower bound for none of these is over 97%. But this here is incorporating all drop heights, right? Which I probably don't want to do that. What I want to do is I actually want to have for the bivariable screen and drop height. And so now what I'm going to get is all 6 parts of my experiment, A, B, and C at the 3 heights. And so, here is where I can go in. And now if I do the confidence intervals, now I have it for every combination of drop height and screen. And here's where you might look to see, do I have any evidence of 97% reliability, even at these different drop heights? And you'll actually see that I don't have 97% even at any of these drop heights, including the half meter. So now here I'm just doing the univariate analysis, but what this case study talks about is making some comparisons. So this is still the bivariate y by x. I just happen to have 3 categories in this case. So my response variable is the outcome. My count is the frequency. Now, I've got 2 things that I can do here. So I can pick drop height as my X factor and screen as my bivariable. So that's one way to do it. And then I'll do it the other way. So I'm just going to switch these around. So now I'll put screen as my X and drop height as my bivariable. And so now I've got the oops, let me move my window here. So now I've got the combination of, do I want to look at the differences between drop heights for each screen? And I'm just going to close all these up just so you can see that I have 3. So I have 3 contingency table analysis, and I can just open up. Oh, I don't know if any of you do this, but when every table and graph in a report is going to have a little gray triangle next to it. And this is nice because it lets you open and close the report window or pieces of the report window, because sometimes it can get, there's a lot of information on it. And especially if you're in class trying to teach, you don't want it to be distracting to have so much. But I can go through here and look at each of these analyses to see if I have a significant result. And it turns out I do for each screen when going across the drop height. So all the results are significant. Yes, drop height has an effect on the success rate for each screen. And then over here on the right, then I have a contingency table analysis that's comparing across screen for each drop height. So I've got the half meter, 1 meter, and 1.5 meter. And you'll see that for some of these, you'll have a significant result. Oh, wait, I have it for all 3. Sorry, I forgot. Okay. So that's one way you can do this. Now, another way you can do this, and I use this approach a lot, is I'm going to go in here and I'm going to run this analysis. You'll see. I'm going to put both drop height and screen as my X. And when I do that, I am going to get the two contingency table analysis, one for screen, one for drop height. Now, I didn't put in a by variable, so this is doing all the screens for all the drop heights or all the heights for all the screens, which isn't really what I want. I want to do this for individual screens or individual drop heights. Well, inside of almost all reports in JMP, I can't think of one that doesn't have it, but there probably is a couple that don't have it. But we have this thing called the local data filter. And what I'm going to do is I'm going to pick screen and drop height as my data filter. And so now you'll see over here on the left, this is what allows me to subset the data, and then all of the reports and all of the analyses in this report window will update to this subset of data. And now this is really handy. And I think this is one thing that makes JMP stand out is in a lot of other software, you have to have a different data table for every subset of data you want to run, whether it's different groups or, oh, I took out a couple outliers and you end up having many data tables, and it can be a little cumbersome to manage. But what's nice about JMP is you can do everything from one data table by just filtering for a particular analysis. So what I can do is, for example, if I go up here in the data filter and click screen A, now what's going to happen now over on the left, that's the screen. So that's trivial, right? That's nothing. Nothing's going on there because I just picked screen A. But over here on the right, this set of analyses is comparing across drop height for only screen A because I said only do the analysis for screen A. So this way I can go through the three screens, and instead of having all of these different reports, I can sort of do the analyses from this one. So I can pick screen, or if I go ahead and pick drop height, now again, over on the right, that's trivial because I'm just picking one drop height. But over here on the left, that's the contingency table analysis, comparing the three screens for that selected drop height. And I can even sort of narrow this down. Like maybe I just want to compare screens B and C at a particular drop height, or screens A and C at a particular drop height. Same thing, I might want to just compare two of the drop heights for a particular screen, and I can go in there and select. So you might find this local data filter very helpful. I sometimes find it helpful when demonstrating analyses for students because you can see all the results change right there. You don't have to open up all these different report windows. You can sit here and just watch results change. And so you can have the students like, hey, keep an eye on the p-value or the confidence interval as I go through these different subsets of data. So you may find that a handy approach. Now, when you drop down the red triangles, you're going to have a menu contextual to that piece of information. Now, watch what happens if I pick, let's say, I'm going to pick only two screens. Now, and I'll pick one drop height. So this analysis right here on the left is comparing two screens, B and C, at the 1.5 meter drop height. If I drop down this red triangle, you'll see that's a different menu than when I had three categories, because now I can say, oh, what analyses make sense for two groups, like relative risk or odds ratio, or testing the difference between two proportions. I have the options as if I did fit Y by X and I only had two categories. So the menus are changing as you're subsetting the data, because I have different analyses that you would run if there's two groups, or in this case, more than two groups. And I can pick those and it would be added to the report. Okay, with that, Ross, do we have any questions that are worth addressing before I go to part 3 of this case study?
Sure, there's one, and I imagine your answer might be we'll see it if we get to the categorical platform, but somebody was just asking about controlling for multiple comparisons in some of these tests.
Yes, let's do that a little bit later. Okay. So let me close this case study here. So again, it steps through some analyses, and this one's demonstrating a chi-square analysis at a particular drop height. It also does proportion comparisons between two. And then at the end, I mean, there's relative risk, there's odds ratios. And then at the end, for the exercises, the students have to run analyses on the ones that weren't demonstrated in the case study. So moving on, I'm going to go to case study number 3, part 3 for this case study. And well, they want to extend this, so they're going to do even more testing. And so now you can see it's a lot of testing here. So now what they're going to do, so remember thus far they did half meter for the 3 screens, 1 meter for the 3 screens, and 1.5 meters for the 3 screens. And now what they're going to do is they're going to add a 4th screen, and it actually turns out it's one of their competitors that also manufactures these screens. So they have some screens from that competitor, and they're going to test. And we're also going to add 1/4 of a meter, 1.25 meters, and then 2 meters, 2.5 meters, and 3 meters. So this is a much larger experiment. And so let me open up that data set. Now, this is illustrating that point I made at the beginning, where having the data in this frequency table format versus having a row for each observation. You can do it like that, but for this data set, I think there'd be like over 1,000 rows because of how many you've tested in each. So this table format, I think, is a little bit more convenient, right? So we've got screens A, B, and C competitor at 0.25 meters, A, B, and C competitor at half, and so on and so on. And then for each combination of screen and drop height, you just have a pair of rows. And as I said earlier, you don't have to have this tested column, and you don't have to have this the rate column. But I'm going to make a graph first that you'll see that I actually am going to use this rate column. So what I'm going to do is I'm going to go into Graph Builder. And so I'm going to put my rate column as my Y. Now, because we have, it's not just that we have so many categories, but drop height is a numeric variable. Now, when we only had 3, like this one up here, we did this as a contingency table analysis. But now that we have so many heights, I probably want to model this with a function. And so this is logistic regression, right? Where we have a numeric continuous X. Because I really want to model the rate of change going across those heights, not just looking at them as just nominal groups. I want to treat that as numeric and I mean, in a way, it's like ordinal. I know they're groups, but I really want to build a function that's treating it as continuous. So again, I'm just starting with a graph. So I'm going to put height on the x-axis, and I'm going to put screen as the overlay. Now, the first thing you might notice is what you might say, wait, this graph looks a little weird. Well, that's because I've plotted both the successes and the failures. So I actually have 2 sets up here. So it's easy to fix that by just bringing up my local data filter, and I'm going to use outcome. And then now I can say, well, what do I want this graph plotting? Do I want it plotting the success rate? And so now it's only using those success rows. And so now I can see those curves. These aren't logistic curves, by the way. They're these spline functions, but it gets the same idea. It's that same kind of shape. I mean, you can adjust how sensitive that spline is. So it's almost like a logistic regression. It's pretty close. Or I can choose to plot it as failures and see that that rate increasing. So this is just what allows me to look at the data, but what I'm going to do is do a logistic regression. And I apologize if you are hearing hammering in the background. There's my house got renovated, and there's a carpenter in the front of the house doing a few things on the fence. So I apologize if you heard that hammering. It shouldn't be too much. Okay, So I'm going to do a logistic regression. And so now I'm going to start off doing it just one at a time. So I'm going to choose the fit y by x. And so my count is my frequency, height is my x, and outcome is my y. And what I'm going to do is I'm going to do that same thing I did earlier, where I'm going to pick screen as my by variable. And now what you're going to get, and I'll just close all the analyses up first so you can see I've got four, one for each screen type. And then if I just open them up, I got the results of a logistic regression. Now we know the success rate is greatly changing across height, so they're all significant, but we could tell that from the graph. So that's not too interesting, because I kind of know that that was what was going to happen. Now, what I'm going to do is I'm going to show you I can run this same analysis, but I can instead use the fit model platform. Now, this is where I can run multi-factor logistic regression. I'm not going to do that yet. I'm going to start off doing that same analysis where I'm going to just run one at a time here. So screen height is my x variable, and screen is my by variable. And now if I can run this right here, and I'm gonna get that same kind of analysis, but this is a more general platform, so I'm actually gonna have more options here. And what I'm actually gonna do, just so you know this exists, JMP has a generalized linear model platform. And the reason why I'm gonna run it this way is because I just wanna show you that this is where you can pick, in this case, different distributions that I'm assuming, and then different link functions that we have here. So this is the most general way you can run logistic regression, even though I'm just running one explanatory variable. And so if I run this, sorry, I forgot to put the outcome in there. If I run this, okay, now I'm just gonna close them all up just so you can see. Again, there's four analyses that were run because of that by variable. And I can open up any of them and see the results. These are going to be the same results as I saw when I did y by x. But the reason why I went here is there's more options under the red triangle when you're in this generalized linear model platform versus just the y by x. And one of the things I wanted to show here is this profiler. And so I'm going to launch this profiler. And now what you get, I don't know if you know this, but any type of graph in a report window, you can grab it and resize it if you want. You can also, move around the axis or rescale it. But I wanted to show this prediction profiler because now I have this interactive tool where I can move across the continuous x variable height, and then over on the left, I'm getting the predicted probability of a success as well as a confidence interval for that predicted probability. And so this is nice. You can either drag this around or just click on it and type in a number, and it will just move that crosshair to that point. So this is, you can see, much better than doing contingency table analysis, because now I can pick any height, even ones I didn't study, and get a predicted probability. The other thing you can do here, which is really nice, is I can do an inverse prediction. And so what I'm going to do is, so the logistic function is predicting the probability for a given height. Well, I can do it the other way around. I can predict a height for a given probability. And so when you click inverse prediction, you're going to get this little window, and you're going to type in the y's, the probability that I'm fixing. And so I'm going to do that 97%, because remember from the very, very beginning, that's the reliability we're hoping to demonstrate. And here what we're going to do is demonstrate which height do we achieve that reliability. So you can see it's just the inverse prediction. Now, I'm also going to just throw in another one just so you can see, you can type in as many as you want here. So I'm also going to just put 50%. So I basically want to estimate the drop height where half the screens are going to fail. And now when I click OK, you're going to get this graph added. And what you're seeing here is, well, you have them both visually on the graph, but you also have them up here as the confidence interval, so I can see the actual values. Now I have the estimated height that achieves that particular success rate. So going back to the original problem where we're looking for this 97% reliability, we can see that we achieve that somewhere between the 0.16 to 0.64 meter drop height. So we can sort of say, hey, some below 0.64, that's where we're achieving that 97% reliability. And it's just showing this visually. Now I can zoom into the graph if I want. So I'm just sort of changing this scale a little bit if I wanted to just get a view of that region of that logistic function. So I think this is really handy because it's pretty common that sometimes you want to you want to go the other way with it. And so, all right. Now what this, oh, hold on, I'm not, something's going wrong with my function here. I can't turn off my, oh, there we go. Okay. Now, this particular case study, what it does is it demonstrates doing individual logistic regression. So it does it for one of them. Again, it's showing what the logistic function equation looks like. It's showing the jump steps. It's showing the analysis output. It's interpreting it. Does it for one of the screens. And then at the end, the exercises has the students do it for the other screens. And so they're building one variable logistic regression models. Now, I'm not going to show this particular case study, but there's a fourth case study. Oh, did I open it? I didn't open it here. There's a fourth case study. And what this one does is it builds a multiple logistic regression model. So that's where you're going to build a model that has both height and screen type. You test for an interaction, and then you build one model that describes all of it, the screen types and the height. That model is going to be more precise, right? Because now I'm incorporating more data when I'm trying to fit that logistic regression function. I don't have time to show that one, but that's how this case study ends, with this fourth part, building a multiple logistic regression model. Now, this one, I like this one because you can work this into class in various points, right? So if you're teaching just one sample, two sample proportions, you can start off with that. And then if later in the class you're doing contingency table analysis, you can go to the second one. And then if later in the class you're going to logistic regression functions, you can go to the third one. And then if you're doing multiple variable logistic regression functions, you can go to the fourth one. Okay, so that wraps up the showing logistic regression. But before I move on, Ross, just want to, of course, do another check-in to see if there's any questions.
Sure, Kevin, thanks. I think there's one thing that would be great to see right now. Somebody brought up, I think this is common in a lot of courses. Somebody mentioned that in fit model, JMP uses effect coding for categorical factors. And a lot of times we actually want to use indicator coding. That might be what we introduced to our students. Could you just show everybody how to pull up the indicator parameterization estimates?
Yeah, so when you are in the report, whoops, I got to open up my file again here. When you are in the report from a fit model, and I already have ones saved, so I'll just open it up here. Under the red triangle, oh, isn't it here, Ross? I'm sorry, let me check. I know I can define contrast and custom test.
I think inside the generalized linear model personality, it's not there, but if you go into the general logistic personality, you'll find it there.
Okay, let's do that. Sorry, I haven't done it from here. I've done it for linear regression. Okay, say again, sorry, Ross, where it is.
So under personality, head back up towards the top. We're just looking for nominal logistic in the in the middle there.
I apologize. I haven't done it in this platform before.
Feel free to go on, Kevin, and I
Yeah, yeah.
will verify where to find that. We can loop back around to it.
Okay, sorry about. Yeah, I know where it is in if I was doing a linear regression model, but I've never done it actually for the logistic regression model.
Or actually, Kevin, I'm sorry. Could you pull that back up one more time? I think we can address it here.
Okay.
Remind me, in that model that you were just fitting, did you have a categorical predictor?
Oh, actually, that one I did not. So
Yeah,
okay,
so that's
okay.
if there is a categorical predictor that you could put in there.
Okay, so let's in this case, I'm showing the full
You
model
might want to
here.
remove that by variable.
Oh, there you go.
There we go.
Okay, run. Okay, so now I've got two factors in there, and
Yep, towards
there
the
it is.
bottom
Okay,
there.
right there. Sorry. Yes, of course. There's no
Well, that's a
here.
simple error there. Of course, that wouldn't be available unless we have
Yes.
a categorical predictor in the model. But there it is, everybody. Thanks, Kevin. I appreciate it.
Oh, yeah, sorry. And that's something which is nice about Jump is it's a little intelligent in terms of the menus. I shouldn't say a little intelligent. It's very intelligent in terms of the menus. You'll only see things that you can do from that point. And actually, I get this a lot, Ross. I don't know if you get that, where somebody will send me a data set and say, "Hey, I'm used to doing this feature or running this little analysis, and I don't see it in the menu anymore." And it's like, oh, well, that doesn't make sense with that data. You can't actually do that. It's illogical, and that's why it's gone. Okay. All right. So with the very end that we have here, first let me mention we have a lot of other modeling techniques. Let me open up this first here. We have a lot of other modeling techniques that you would do with a categorical outcome, like partition or neural networks. K-nearest neighbors is one. Support vector machines is one. Discriminant analysis is another one, except discriminant analysis we put under the multivariate menu. And that's because when the math was developed for that, I think almost 100 years ago, it's technically mathematically a multivariate technique because it treats it as multivariate response variables, but technically that's just another modeling technique. So sometimes I think it should be here as well, but it's under the multivariate menu. But those are all other modeling techniques where you can try to predict a categorical outcome based upon factors, whether the factors are categorical themselves or numeric or both. So what I'm going to do is I'm going to finish off with this little time we have left by opening up a data set and where I can show Jump's categorical platform. Okay, so this data set is the result of a survey. And so we have 448 responses. And basically it's a survey about people's careers. And so what we have is a set of variables that are characteristics of the responders, right? So things like their gender and their age and their income and how long they've been working at their job, salary. And then we have the results of a survey where they're asked different questions. For example, are you working on your career? Do you want to see the world? Do you have interests outside of work, et cetera? And everything is either agree or disagree. Something I should point out. Some of these variables, like age is one of them. Years being employed is another one. Make this a little bit bigger so I can cover it all. So years of employment, as well as years in that position. Salary is another one. Notice that we have the data both as numeric continuous as well as categorical. And I had pointed that out at the beginning that that's kind of common. Well, if you need to create those categorical variables, it's really easy to do it. So what you would do, there's two ways I can show. One is if you click on the column and go right click and click recode, you're going to get this window that's going to appear. Now it's going to show a value. It's going to show each value in that numeric continuous variable. We don't have too many here, but if you had a lot, then this isn't the best approach. I'll show you another one in a second. But what you can do is you can grab a group. So I'm going to grab 25 to 29. I'm going to hit group, and I'm going to say change that so that it says 25 to 29. Now jump is, when I do that, jump's going to say, well, now I'm turning it into a character variable, just to confirm that. And so I can walk through here and just create all these new groups. And if I said recode, I would get that, that new column, this age, group, and years. The other way you can do it is if you click on the column and you go here under utilities, and I click make binning formula, it's going to pull up this little interactive window. Now jump's going to start with a default set, but I can go in here and create where I want the categories dividing. I can add more categories, but what I can also do is I can interactively drag this around, and now it's picking the cutoff points, and I get to actually see what the count is in each of those. And I can delete these, or I can add cut points. And if I hit make formula column, then it's going to make a formula column using a conditional if then, and then I would get any one of these I'm doing, age group or employee tenure. So that's kind of a common thing to do. Okay, but I wanted to show this one platform. This is a really large platform. So I encourage you to go to the JMP's help for categorical because there's a lot that you can do here. I'm just going to demonstrate one particular analysis. So basically, I'm going to be doing cross tabulations, but I'm going to have more than one factor. So it's beyond that basic chi-square analysis I showed you. There's many ways you can have this data, and it's very common in survey data that the data is formatted in all these different ways. I'm just going to demonstrate one of them. So what you can do is I can actually build this table. So for example, let's pick, I'm going to pick a couple of these responses. I'm not going to do them all. Let me just, well, I'll do them all. Why not? I'm going to come over here and I'm going to drag this and put it there. And then I'm going to grab a couple categorical variables. I'll just do gender and age group. And I come over here and I'll say, put them on the top. Oh, actually, no, sorry. I don't want to do that. Let me delete. What I actually want to do is I want to put age group inside of gender. That first way I would have done it, it would have had a separate one for gender and age group. So you see how I have age group inside of gender. So I click this add button and it's going to come over here and put that structure, and I can go and bring it back if I want to edit. I can also save and do more. And when I click OK, what I'm going to get is this large cross tab, and you will see at the top, I've got that age group and gender. And then over on the left, the rows are corresponding to those different questions I have. And so I've got the counts and the rates of agree and disagree. Now I'm going to do this one thing here. I'm going to show the letters. And so you see across the top, I've got A, B, C, D. You'll see why that I need to do that. And if I go in here, oh, actually, I'm going to add the chart there. So I could, there's some graphs I could add if I want. But what I'm going to do is I'm going to run some tests. And so now I've got tests that's testing across the age group and gender for those different questions. Let me see what else. I can compare each sample. And so what this is going to do is it's actually going to compare the different gender and age group for these questions. And if you've done crosstabs before, you're probably familiar with this, is there's so many comparisons. In fact, let me grab that where, I'm going to go compare each cell. Down at the bottom, it's going to show every possible combination. So you can think of how many tests there are, right? I get A versus B, A versus C, A versus D, dot, 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 right? All the way to the final one. So that table is very, very large. This allows you to go in and look at individual p-values, but a convenient way it's done up here in this table is it's using this letter coding to show you, is that cell statistically different from what other cells? And it's using this technique of uppercase, lowercase to say if it's significant at the 0.05 or 0.01 level. And so this is, you see, I made a very large table there. So that's why there's so many comparisons. So this platform really lets you generalize this. Now, if I go back here for a second, I'm just going to put this back. If I rearranged it the other way, where I put these questions, if I put those at the top and the gender and age group on the left, then it's going to run it with sort of the inverse way. And my comparisons would be going not across the age group and gender, but it would be going across those questions. So there's all sorts of combinations you can do here. And this is a very, very large, very large platform you can do here. And that question that came up earlier, this is a platform that would allow me, because in this case, it really would matter, is I'm doing so many comparisons that I can actually run an adjusted p-value. It's that FDR stands for false discovery rate. So this way it's going to adjust based upon the fact that I'm doing so many comparisons, and the p-values will get adjusted for that. So you can see I've got added to this, I've got these FDR p-values added.